Good morning. Today we are continuing our topic, our module, nuclear detectors and counters. And here we are discussing cloud chamber and bubble chamber. So the first topic is cloud chamber. It's also known as Wilson cloud chamber because C.T.R. Wilson was the person who first designed this. So Wilson cloud chamber was invented by Charles Thomson Rees Wilson, that is C.T.R. Wilson, in 1911. So hence the name Wilson cloud chamber. And cloud chamber is an instrument which is used for the visual observation of the tracks of the charged particle when they pass through matter. So it is an instrument which is used for the visual observation of the tracks of the charged particle in their passage through matter. And this device is used to observe the path of ionizing particles such as alpha, beta and gamma radiations, and also to detect the different type of nuclear radiations. We can detect and also observe the path of the ionizing particles using this Wilson cloud chamber. Now, what is the principle behind this cloud chamber? When a particle is passed through the supersaturated vapor, droplets are formed on the line due to the ionization along the track and the particle is detected. I repeat, when a particle is passed through supersaturated vapor, droplets are formed due to the ionization along the track and thus the particle is detected. Let's move in detail. So this is the construction part where you can see a chamber which is closed. So it is a large airtight cylindrical chamber with walls. You can see both the walls here, and the ceiling is made up of glass. That means a glass plate is inserted as the ceiling. And this chamber consists of dust-free air which is saturated with water vapor or some other liquid. So the chamber consists of dust-free air saturated with water vapor, and this mixture inside this chamber can be compressed or expanded using this piston, and this piston is covered with a black felt. You can see the picture of the black felt in the next slide. Black felt is used so that no light is reflected from it. So it is black felt, isn't it? So there is no reflection from its surface. So here is a path for the light beam and also there is a radioactive source is here. So let's move on to the writings. It consists of a closed chamber with a glass cover at its top and a movable piston at its bottom. There are two windows, that is for light source and for radiation entrance. See, a camera is also fitted over the glass. So here this is a glass plate, isn't it? A camera can be fitted here so that we can see the path of ionizing particles through this glass plate. Alcohol is placed in the chamber. See, we can use any volatile liquid along with the air, isn't it? So alcohol can be also be placed inside. So that is a construction. So again, so this is a light or lamp from which the light will enter into the chamber. This is the radioactive source which produces the radiations. So whenever this radiation enters this chamber, what happens? Ionization of the particles takes place, and the chamber consists of what? Alcohol vapor, and alcohol vapor condenses to form liquid droplets around this ionized molecule. And this is the filtering I had said earlier, filtering, which is made up of black color so that no light is reflected from it. And below this you can see a dry ice which cools the alcohol vapor until it is saturated. So the alcohol inside this chamber is in a saturated condition. So what happens when a radiation from the source enters the chamber? This radiation will ionize, and the ionization molecules will become the centers for condensation, alcohol vapor condensation. So the condensation of alcohol vapor will occur on the ionizing particles, and thus the liquid droplets are formed and it can be photographed. So let's move on to the working. So initially the piston is pulled down rapidly. Pulled down means as a result of which the mixture will undergo adiabatic expansion. Adiabatic expansion means the temperature will fall, so that the mixture becomes supersaturated with the vapor. Supersaturation means it is in a situation that so that there is no condensation will occur, but it is ready to undergo condensation. Such a state is known as supersaturated state. So first what we are doing is that the piston P is moved suddenly down. Here you can see an arrow here. So the piston is moved down. So adiabatic expansion takes place inside this so that the temperature decreases, and at this reduced temperature the mixture inside the chamber will become supersaturated with the vapor and remains there without any condensation of the vapor, so that the mixture is ready to condense, but there is no condensation occurs till now. Now what happens when an alpha or beta particle interacts with the mixture? So here we are having a radioactive source. From this either alpha, beta or gamma particles will enter the chamber. So what happens? This radiation, nuclear radiation, will ionize the mixture inside the chamber. So ionization means ions are formed. Positive ions as well as negative ions are formed. And this resulting ions act as the condensation nuclei. Condensation nuclei means now on this ions the condensation will take place. So these charged ions can serve as the nuclei of condensation of water droplets. So the resulting ions act as condensation nuclei around which a mist will form. A mist means the condensation. See, here you can see this is an electron, negatively charged ion means it is an electron, isn't it? And around this electron, the mixture is ready to condense, isn't it? So the condensation will take place after ionization on the, and this condensation will take place on the ions. So here you can see the bubbles. So it is a condensed part, condensed nuclei. So because the mixture is on the point of condensation, the mixture will condense on the ions, so that the charged ions serve as the nuclei of condensation. So the supersaturated vapor will condense in the form of fog on the dust particles as well as the ions produced in the chamber. We are taking dust-free air inside it. Even though if there is any dust particles, the condensation will take place on that dust particles, and also the condensation will take place on the ions produced. So here you can see the bubbles. So these bubbles can be photographed using a camera. Photograph is taken on that time. So thus we can see the path of the particles inside the chamber. So that the cloud chamber is used for the visual observation of the tracks of the charged particles when they pass through matter. I repeat the working. Here we are having a piston, and here inside the chamber is filled with a mixture, and that mixture is in a supersaturated condition. That means it is ready to condense or ready to undergo condensation. And now the radiation enters through the into the chamber using this source, and when radiation enters this chamber, it ionizes the particles and a positive and negative ions are formed. So whenever this positive and negative ions are formed, the mixture will undergo condensation on this ions, so that we can see the ions. Ions serve as the nuclei of condensation, and thus this can be photographed using a camera, and we can visualize the path of the charged particles when they pass through the matter. So this is the different tracks of the alpha, beta and gamma radiations. We know that inside we are using a radioactive source. So this radioactive source will emit either alpha radiations, beta radiations or gamma radiations. So the trace of this alpha, beta and path of this alpha, beta and gamma radiations can be seen inside this cloud chamber. Now this cloud chamber has many uses. It is used to study the behavior of individual atoms. Also, it is used to study the process of ionization. So, it will be good to study these two uses of this cloud chamber, that is to study the behavior of individual atoms or also to study the specific ionization. And it has a small disadvantage also. See, in order for the starting condition, we had moved the piston downward, isn't it? So that the mixture is undergoing adiabatic expansion, and we are having this process. Now, once this process is over, we need time, a definite time, to recover into its initial state. So that is the main disadvantage of the cloud chamber, that this cloud chamber needs a definite time to recover after an expansion. So that is the first disadvantage. And the second disadvantage is that it cannot be used for detecting high energy particles. We had already said that we can visualize the path of the charged particles, but high energy particles path cannot be detected easily in a cloud chamber. So two uses as well as two disadvantages are there. Uses to study the behavior of individual atoms and to study the specific ionization. And disadvantages are that the cloud chamber takes a definite time to recover after an expansion. Second one, it cannot be used for detecting high energy particles. So that's about the cloud chamber. Now we are moving to the next topic, which is similar to that of the cloud chamber, that is bubble chamber. And bubble chamber is a high energetic particle detector. We had said that this cloud chamber has a disadvantage that it cannot be used for detecting high energy particles. So bubble chamber is designed so that it can detect high energetic particles. So that due to the disadvantages of cloud chamber, Donald Glaser in 1952 invented the bubble chamber, and he discovered this at the University of Michigan in 1952. It was said that he got the concept of bubble chamber while he was drinking beer. But we can say that he was not inspired by beer, but he used that concept in the formation of this bubble chamber. Bubble chamber, it is similar to cloud chamber, but it uses a superheated liquid as opposed to a supercooled gas. See, in cloud chamber we are moving the piston downwards so that the adiabatic expansion occurs, so that the temperature get reduced, isn't it? So the gas is in a supercooled state. But here in bubble chamber we are using a superheated liquid. Superheated liquid means it is ready to boil, but it's not boiling. So that is a superheated liquid. So it uses a superheated liquid instead of vapor as that of a cloud chamber. Again, we are using this method of visualization of tracks of the charged particles. See here in the picture you can see the blue lines. These blue lines are the path of the particles, charged particles. So these particles passing through the liquid leave tracks, and these tracks can be photographed using high-speed cameras. Again, also pistons are used in this bubble chamber in order to adjust the pressure rapidly. And when compared with a cloud chamber, it has significantly increased rate of collisions inside the chamber. So that is a figure showing the bubble chamber here. And these are the path of the charged particles, which is photographed. So again, bubble chamber is a vessel filled with superheated liquid. Often we use liquid hydrogen. So we are using a superheated liquid, it is used to detect the charged particles moving through this liquid. Again, this is made up of a large cylinder with a liquid which is heated to just below its boiling point. So inside in the cloud chamber we had a mixture of a gas inside the chamber. Now we are taking liquid inside this chamber and it is heated in such a way that it is ready to boil. So it is heated just below its boiling point. Now as particles enter the chamber, the piston is moved downwards so that the pressure is decreased and the liquid enters into a superheated state. Again, the radiation enters the chamber, it ionizes the particles and the liquid vaporizes on this ion particles, forming microscopic bubbles. So that this chamber is known as bubble chamber. I repeat, we are moving the piston downwards so that the pressure is decreased, so that the liquid inside the chamber is in a superheated situation, so that whenever the charged particles enter this chamber, it undergo ionization and this liquid vaporizes on these ions, forming bubbles. And these bubbles can be photographed and can be studied. So here you can see this is a cylindrical chamber and the piston is given here and the camera is fitted above. The particles can enter through this direction, so that when the piston is moved down, the liquid will be in a superheated state, and when the particles enter, it gets ionized and this liquid will vaporize on these ions. So in cloud chamber, condensation occurs on the ions. Here bubble chamber, vaporization occurs on the ions, forming bubbles. So that is the principle of the bubble chamber. When a charged particle passes through superheated liquid, it leaves a trail of tiny gas bubbles that can be illuminated and photographed. The track of the charged particle can be used to identify the particle and to analyze complex events. So again we can move on to the conclusion. So it's a vessel filled with liquid hydrogen at a temperature above the normal boiling point, but held under a pressure of about 10 atmospheres by a large piston to prevent boiling. See, the liquid is heated at high temperature, so that, but it is held under a pressure so that no boiling will take place. And when the particles enter, the piston is moved downward to reduce the pressure, allowing bubbles to develop along particle tracks. After about 3 milliseconds have elapsed for bubbles to grow, tracks are photographed using flash photography and also using several cameras. The piston is then moved back to recompress the liquid and collapse the bubbles before boiling can occur. So invented by Glaser in 1952, the bubble chamber is a high energetic particle detector. So various liquids have been used in this bubble chamber. Glaser has used ethyl ether. Later liquid hydrogen, deuterium and helium also used in this chamber. Heavy liquids such as pentane, propane and xenon have also been used in this bubble chamber. So that's about bubble chamber and cloud chamber. You have to mention the principle, working, construction and its uses and disadvantages. I hope the session is clear to you. Thank you.